Mesh analysis is a method of analysis that is used to simplify circuits. Now, mesh analysis comes in two ways. One is the mesh analysis general approach, and the other is mesh analysis format approach. Format approach is basically a shortcut for mesh analysis. First, we'll start with the general approach. The steps for the general approach is: first, we assign a distinct loop current in the clockwise direction to each closed loop of the network. Now, what does this mean? As you can see, let's visualize that step one with this question. Now, every network will have multiple loops, and you have to first identify the loops for mesh analysis. And each loop has to be assigned a loop current, an imaginary current has to be assigned, and in any one certain direction. It can be either clockwise, all of them must be clockwise then, or it can be anti-clockwise, then all of them must be anti-clockwise. Every loop must have an anti-clockwise loop current. So all loops must have the same direction. The reason we usually use clockwise is because it just makes life easier. Anti-clockwise can be used as well, but whatever is used, it has to be consistent throughout all the loops. Now, step two is to assign polarities to each component of the closed loop. So the sources will have their usual polarities, the larger side positive and smaller side negative. As for the resistors or the loads, we can assign them either positive negative or negative positive polarities. And whatever we assign, it must be consistent throughout the circuit. Now, the important assumption during this assignment is that if the assigned loop current must enter each resistor from the same polarity. So let's say in R1, our first resistor, the loop current enters through the positive side. Yes. So this means every single resistor in the circuit must also have their loop current entering through them from the positive side. So as we can see in R2, positive side, R3 entering through positive side. So this has to be consistent throughout the network. And notice that R2 has two sets of polarities, plus minus here and minus plus here. This is done to maintain that consistency of the loop current entering through the positive side. As you can see, the loop current I1 enters R2 through the positive side here in the left side. But in the right side polarities, the loop current which starts from B enters R2 again from the positive side. So to maintain this consistency, every resistor that is shared between two loops will have two sets of polarities. And step 3 is to apply KVL to our Kirchhoff voltage law to each closed loop. And step 4 is to solve the equations that we will get after applying KVL to each loop. Now each loop will give us one equation, so the number of equations equal to the number of loops. Now let's start solving this question to clarify all the steps. Now step 1 and 2 is done. Here the loop currents are assigned and the polarities are assigned. So we start from step 3, which is applying KVL. First, let's apply KVL to loop number 1. Now, before starting, we have to remember one thing. We have to assume things before for mesh analysis. And the most important assumption is assuming the signs, polarities, plus or minus. Now, we can assume either that we can have an opposite assumption. Opposite assumption as in, if the current is entering through the negative end, as is being done in E1, then we write a positive sign in the equation. So we write plus 5 volts because the current is entering through negative end. And again, if the current is entering through the positive end of a resistor or source or whatever, we write a negative value in the equation. So opposites. So we're at minus 1. We can assume this, the opposite assumption, or we can assume the same assumption. That is, if current is entering to the negative end, then we write a negative value, so negative 5 volt. If the current is entering through the positive end, then we write a positive value, so plus 1 ohm. So we can assume either one of this, but whatever we assume must stay consistent throughout the network. So every single component should be calculated using the same assumption of positive or negative, either opposites or the same values. Now that is out of the way, let's start solving this. So for loop 1, I personally like to use the opposite assumption. So for E1, I'll be writing plus 5 volts because the current is entering through the negative end. So 5. Then for R1, it's a minus. So we write the voltage KVL. So V is equal to IR. Now R is 1 ohm. So we'll write I1. Just I1 because we don't have to write 1. I1. Then for R2, again negative because current enters through the positive end, minus R2, and then since R2 has two currents flowing through it but in the opposite direction, so I1 and I2 are flowing in the opposite direction through R2. As you can see, I1 is going down and I2 is going up, right? So we will use the resultant, which will be I1 minus I2. And since we are doing this this equation is for the loop number 1, so we are assuming I1 to be positive. When we will be making the equation for loop number 2, we will assume that I2 to be positive. And lastly, we have E2 in loop 1, so that's minus 10 volts because it's entering through the positive end. Minus 10 is equal to 0. Now let's substitute the values. So 5 minus I1 minus R2 is 6. So 6 times, let's just remove the brackets directly. So 6 I1 and then plus 6 I2 minus 10 is equal to 0. Now let's arrange them and bring I1 to the front. So I1 minus 6 I1 is minus 7 I1. Then plus 6 I2. 5 minus 10, that's minus 5, is equal to 0. So this is our equation 1. Let me put that in a standard format. So minus 7 I1 plus 6 I2 is equal to 5. That's equation 1. Now let's make the equation 2 from loop number 2. So the first loop number 2, for loop number 2, the loop current I2 starts from point B, right? So the first component is E2 and it will be positive because current in the loop I2 enters E2 through the negative end. So 10, first we put 10, and then R2, so minus R2 times I2 minus I1. See, so for loop 2 we put I2 as the positive value, and then we have R3, which will be negative again, so minus R3 is equal to 0. Now let's substitute the values. So 10 minus R2 was 6. Let's remove the brackets. So 6 I2 plus 6 I1 and minus 2 I2. R3 will be 2 I2. Right. Wait, this will actually be VR3, not R3, because we are this is KVL, not just, we are taking the voltage values, not the resistor values. Yeah, so here also it should have been VR2, not just R2. Yeah, the rest are okay. And here, yeah, the rest are okay. Okay, so VR3 is equal to 0. Minus 2 I2 is equal to 0. And let's rearrange them and bring I1 to the front. So 6 I1 minus 8i2 minus 6i2 and minus 2i2, so minus 8i2 equal to minus 10. Right, that's equation 2. Now we have two linear equations. Now let's plug them in the calculator and solve them. I'll make a separate video showing how to solve linear equations in the calculator. But for now, just plug them in. Equal to minus 10. First equation 1. So minus 7 plus 6 and then 5. And equation 2 is 6 minus 8 minus 10. So I1 is 1 amperes and I2 is 2 ampere. That's our answer. Now let's do another question. So again we have 2 loops, and the loop currents are assigned I1 and I2, both in clockwise directions. Now remember, if the loop currents are not assigned, you have to assign them yourself, and you can assume any direction you want, as long as you stay consistent for every single loop. And same with the polarities of the components, which are also assigned here. You can assume anything as long as you stay consistent with your assumption. So let's start with loop 1. KVL in loop 1. We have E1 first, which will be minus, because I assume it in the opposite direction. So minus 6, and then VR3, so VR1, so minus VR1, and then again E2, so that's minus 4, and R2, which will be minus again, minus VR2, not R2, minus VR2 times I1 minus I2 equal to 0. All the steps are same. It's the same question, just different values, and the shape looks different. This was a square and this is a triangle, but that does not matter, because if you notice, the components are all connected in the same ways, so it's all the same. Now we have minus, let's substitute the values. So minus 6 minus VR1 will be minus I1 and R2, so 2I1, and then 4, then minus VR2, which will be, wait, this won't be VR2, sorry, it's be just R2, because we are taking the current values. I made the same mistake here, not here, but here, yeah. This won't be V, because R and I makes V, but this one was VR3, this will be VR3. Okay, now let's continue. So R2 was 4 ohms, so 4 times I1 minus I2. Let's just remove the brackets. 4I1 plus 4I2 is equal to 0. Now let's rearrange and bring I1 to the front. So minus 2 and minus 4, that's minus 6I1 plus 4I2 is equal to minus 6 minus 4 makes minus 10, so plus 10 on this side. That's equation 1. Now let's form equation 2 from loop 2. For loop 2, the first component is R2, so we will have R2, and it will be negative because entering through the positive side. So R2 times I2 minus I1. For loop 2, I2 will be positive. And then we have E2, which will be positive because entering through the negative side. So plus 4. And then VR3, which will be negative because entering through the positive side. So minus VR3, and then we have E3, which will be negative again. So minus 3 volt. Minus 3 is equal to 0. Now let's substitute the values. So R2 is 4 ohms. 4 times I2, remove the brackets. So 4I2 minus 4I1 plus 4 minus VR3. What is VR3 again? R3 was 6 ohms. So 6I2 minus 6I2. You don't have to write VR3 like this. You can just write the values directly. I'm writing VR3 to make sure there's no confusion left. So minus 6I2 and then minus 3 equal to 0. Okay, so now let's bring I1 to the front. That's minus 4I1. Yeah, minus 4I1. And then, wait a minute. R2 will be negative here. Yeah, enters with the positive side. Why did I put positive? So minus R2. Okay, so this will be minus 4I2. And this will be plus 4I1. So this is plus 4I1. Yeah, the rest are okay. Minus 4I2 minus 6I2, that's minus 10I2. And then 4 minus 3, that's plus 1. Send it to the right side, so minus 1. That's our equation 2. Okay. Now let's solve it with the calculator. Again, 2 linear equations. So we have minus 6 plus 4 equal to 10. And then plus 4 minus 10 minus 1. So we have I1 is equal to 2.18 minus 2.18 ampere. Minus 2.18 ampere. And I2 is equal to minus 0.77 amperes. Now this minus directions and this minus signs, they basically mean that the real currents are opposite of this assumed loop currents. So I1 is clockwise, but in reality I1 we assumed it as clockwise, but in reality it is anti-clockwise, and that's why we get a negative value of I1. And the same for I2. But this doesn't mean that you can go away without writing the negative signs in the answers. In the exams, the answers must have the negative signs if you find your calculation to give out negative signs. So that's it. Now let's go to a new concept, not new, a modified version of the mesh analysis, the super mesh current. Now, mesh analysis is done by applying KVL. So we need the voltage sources in the network. If we have a current source, the easiest way to apply mesh analysis is to first convert that current source into a voltage source, like I showed source conversion in the previous video of source conversions. But for doing that, we need a resistor. We need a resistor in parallel with the current source. However, sometimes there will be a current source without a parallel resistor, like you can see here. So like this current source, it does not have a resistor in parallel with it. So we cannot convert it into a voltage source. So how do we solve it? How do we solve this circuit? This is where super mesh current comes in. Now, step 1 and step 2 of super mesh current is analysis also is the same as mesh analysis. So step 1 and step 2 is the same throughout the board, even for format approach and super mesh. Now step 3 is different for super mesh. Now remember, super mesh is applicable only when you have a current source without a parallel resistor. So basically, you cannot convert the current source into a voltage source. So what you do for step 3 is for step 3 you remove the current source. Okay, remove the current source mentally, and you can redraw the circuit if you want for simplification. Now, as you practice, you will not need to redraw the circuit. You can do it all in your head, but for explanation I'll just redraw the circuit to make it easier to understand. So this is the circuit. Okay, here's the grounding. Now notice there is no current source. Okay, we remove it and it's a short circuit. It's a closed open circuit, not short, it's an open circuit. So, but we will have our assigned loop currents. Okay, even though it's an open circuit in the middle, we still have two assigned loop currents, I1 and I2. All right, both in the same direction. So this was step 1, remember? The step 1, and the polarities are assigned. That's step 2. I won't be writing the values here, we can just use it from the image here. So step 1 is the same as normal mesh analysis. You assign the loop currents. Step 2, you remove the current source, and you can do it in your head with enough practice, but now as for the first time, for easy explanation, I'm redrawing the circuit with a remove current source. So that's step 3. Okay, after polarities, yeah, step 2 was polarities, and step 3 is removing this. Now step 4 is to make a single equation using both the loop currents. Yeah, in normal mesh analysis we make two equations for two loops using two loop currents, but in super mesh we will make a single equation using both the loop currents. Okay, so I'll draw that. I'll change the color. Okay, let's write that now. So again, we'll start from here. Okay, starting from here, there will be loop 1, and then loop 2 will be like this. So this voltage source is here, E1 20 volts, and current enters through the negative side, right? So I'll put a positive sign, so 20 volts. And then R1, VR1 will be, wait, okay, the polarities are not assigned. Let's assign the polarities. I'll just put plus minus, plus minus, plus minus. Okay, so now after 20 I'll put a minus because the loop current is entering the positive side, right? Plus minus, plus minus. Yeah, so enter the positive side. I'll write 6I1. Then R2 is again under loop current 1, so and plus some minus 4I1. Then we go to the first resistor for loop current 2, which is 2 ohm, this R3 here, and also current headers through plus, so I'll put minus again. So minus R3, and the value is 2, and then I2. Okay, not I1 because it's under loop current 2, so I2. And then we go to the last component, which is the E2, source E2, and enters through negative, so I'll put a positive here, plus 12 volts equal to 0. Okay, that will be our first equation, but first let's rearrange it. We'll bring I1 to the front. So minus 6 minus 4, that's minus 10 I1, and then minus 2 I2, then 20 plus 12, that is 32, with plus, I'll send it to the right side, so minus 32. So that's our equation 1. Now what about equation 2? So for equation 2 is step 5. So step 5 is to bring back the current. Okay, we already have it in this figure, but if you wanted to redraw it, you would redraw again and redraw the current source. Okay, so that's how you bring back the current source, 4 amperes, and you make another equation using Kirchhoff's current law, KCL, using a loop current I1, loop current I2, and the current source itself. Now, if you remember from the KCL and KVL video, for KCL, the current entering a node will be equal to the current exiting a node. Yeah. So if we use this node as a reference point, okay, let's say it's node A, or just write N1, node 1. Okay, if we use this N1 as the reference point, then we can see that loop current I1 is entering the node, the main current source I is exiting the node, again loop current I2 is going this way, so it's exiting the node. So we can write I1, loop current I1 is equal to I plus I2. This is entering the node, exiting the node, and this is our equation 2. Okay, actually wait, let's just rearrange this. I'll write it here. We want I1 to be at the front, so I1 and then minus I2, matching the format, so it'll be easier to solve in the calculator. I1 minus I2, and I is 4 ampere, right? 4 ampere, so we'll write 4 here, is equal to 4. This is our equation 2, not this. Same thing, but just rearranged. Okay, now let's put that in the calculator. We have 2 linear equations, so we can find I1 and I2. So minus 10 I1 minus 2 is equal to minus 32, and then I1 is 1 minus 1, 4. So we have I1 is equal to 3.3 ampere. I'll write the answers here. I1 is equal to 3.33 ampere, and I2 is equal to minus 0.67 ampere. That's our answers. So that's the supermesh current. Just a few different steps, but mostly same. Okay, we have another supermesh question. So again, note. So let's follow the steps for solving this question. Step 1 is to assign loop currents, which we will do here. Let's assign loop currents I1 clockwise, I1, and loop current I2 clockwise again, and then loop current I3 clockwise. Okay, and the polarities, so plus here, minus here, and then again plus here, minus here, plus, minus, plus, minus, plus, minus. Okay, now let's start solving. Now remember, for step 3 we are to remove the current sources for supermesh, like I showed here. I won't redraw this one, but that will be enough. Redrawing is a hectic process. Just learn to do it in your head. We have to learn it. Now, if we remove 6 ampere, these two sources, 6 and 8 amperes, then notice that these two loops become invalid, right? I2 is the only loop that remains. So we will get one equation from here. Let's make the equation. It will be minus V 2 ohm. So that will be minus I2 2I2 minus 2I2, and then minus 6I2, and then again minus 8I2. Wait, no, there's a mistake. Okay, let's fix that. So it will be minus R, let's just take R 2 ohms, okay, and then even though the loop currents 6 and 8 ohm is removed, the loop currents are there, so two currents are passing through 2 ohms, I1 and I2. Since we're doing for I2, it will be I2 minus I1, right? So I2 will be positive, I2 minus I1, and then 6 will be just that I6I2, and then again a negative, and 8 in bracket open, and I2 minus I3. So I2 minus I3 equal to 0. Now let's remove the brackets. So minus 2I2 plus 2I1 minus 6I2 minus 8I2 plus 8I3 is equal to 0. Okay, let's just rewrite that here by bringing I1 to the front. So we have 2I1, and then minus 2 minus 6 minus 8, that's 14, so minus 16 I2, minus 16 I2, and then plus 8 I3. So plus 8 I3 is equal to 0. That's our equation 1. Now if we look back at the question, we can see that loop current I1 is actually just the 6 ampere source. So we can write I1 is equal to 6 amperes. Similarly, loop current I3 is just this source 8 amperes. So I3 is equal to 8 amperes. Now if we substitute the values in equation 1, then we have 2 into 6, right? So 12 minus 8 into 8, so minus 64. So it will be plus 64. And here we have minus 16I2. Minus 16I2 is equal to 0. Now we have just one unknown variable, so we can just calculate that without having to solve linear equations. So minus 16I2 is equal to 64 plus 12, which is 76. 64 plus 12 is 76. And then it'll be minus 76 here. Then minus and minus is cancelled. So I2 is equal to 76 over 16. 4.75. 4.75 ampere. Done. Now we have mesh analysis format approach right here. Okay, now format approach, like I said before, is basically a shortcut for mesh analysis. Okay, so step 1 and step 2 is the same as general approach up here. So first we assign a distinct loop current and then assign polarities, which are already done here. Now before applying, we will apply KVL, but in a different way. So instead of making two separate equations, we can make two equations at once. What we do is first we take the loop current, write the loop current of loop 1, okay, I1, then open a bracket, add all the resistors within loop 1, so R1 plus R2, that's all we have, right? Now minus I2, okay, now why I2? Now we go to the second loop and we'll bring I2, but for the resistor that is being shared between both loops, so which is R2, so we'll write I2 times R2, that's it, no other resistor, equal to the total voltage sources that we have. So we have 5 volt here and 10 volt here. Now will we add them or subtract them? Now notice that we have E1 minus plus and then E2 plus minus, right? So basically they're placed like this, plus minus, and then wait, no, that's not how they're placed. They're placed like this, minus, plus, minus, this is 1, and then they're placed again like this, okay? So plus here and plus here. When it's this situation, it will be minus, so E1 minus E2, okay? But if it was minus to minus, so say we have 1 here, ignore these parts, let's start from here. So this is plus, okay, plus here, minus here, right? Now if we go like this, and we have another plus here, minus here, okay, so minus and plus is in the same side. This would be E1 plus E2, but we don't have that. We have this, E1 minus E2. So we'll write 5 minus 10, so minus 5. And then substitute the values, so I1 times R1 plus R2, that's 1 plus 6, minus I2 and R2, so 6I2 is equal to minus 5. So finally we have 6 plus 1, 7 I1 minus 6 I2 is equal to minus 5. So this is our equation 1. Okay. Equation 2, we'll do the same thing, but first we place I2. Actually place I1 first, it'll be easier, but make sure it's negative. Why? Because we're doing for loop 2. For loop 2, I1 will be negative, and for loop 1, as you saw here, I2 was negative. I1, and then place the resistor that was being shared between both loops, so R2, 6 ohm. Put the value directly, 6. Okay, I1 6, so basically 6 I1. I can just erase that and write 6 I1, okay, and then put a plus. I2 will be plus for loop 2, so I2 in the bracket, add all the resistors within I2, so R2 and R3, 6 plus 2, which is 8, right? Again, we can just, it will be 8 basically like this, but we can just write 8 I2, okay, equal to, again, add all the voltage sources, but there is only one which is positive because entering through the negative side, so we'll write positive here, 10 volts. Now carefully observe this, that equal to, and then on the right side we wrote positive according to our assumption. We didn't write it in the left side and then shift it, okay? If this is how we write it in format approach. If you want to shift it to the left side, you can bring it to the left side and put a negative sign, but we don't need to do that. So this is equation 2. Now here we have two proper linear equations, and it's much easier and much faster to get this two equations for mesh analysis in the format approach. Okay. A lot of work has to be done in the head though for this, so it needs practice. But once you nail the technique down, It's a lot easier and a lot faster than the general approach. Saves time in the exams. So now we just plug in these values in the calculator and solve the two linear equations. 7 minus 6 minus 5, and then 6, 8, 10. So for I1 we have 0.2. I1 is equal to 0.22 amperes, and I2 is equal to 1.1 ampere. 0.1 ampere. That's it. Now let's do another one with the format approach. We have some more practice questions, so I'll be doing them all with format approach because that's the easy. It saves a lot of time and it's more of the standard approach because it saves time. That's it. General approach is for beginners and format approach is for the pros. So again, let's start with loop current 1. Step 1 and step 2 is done here. So I1 will add them up. So 8 plus 6 plus 2. 8 plus 6 plus 2. And then minus I2 and 2 equal to, there's only one voltage source which will be positive, so plus 4. Let's simplify this. 16 plus 14 plus 2, 16, so 16 I1 minus 2 I2 is equal to 4. That's equation 1. Now equation 2 will be, again we write minus I1 and just 2. We didn't need that bracket, but it is what it is. Then plus I2, so yeah, I2 times 2 plus 7, all the resistors, equal to all the voltage sources, which is 9 volt, there's only one, and it will be negative because interest to the positive side, so minus 9. Okay, let's simplify that. So minus 2 I1 and plus 2 plus 7, so 9 I2 plus 9 I2 is equal to minus 9. That's equation 2. Now just plug the values in. 16 minus 2, 4, and then minus 2, 9, minus 9. So I1 is 0.13 ampere. I2 is minus 0.97 ampere. That's it. See how fast format approach was. Now let's do another practice question. So we have 3 loops here. Again, we can do this with the format approach. So we start with loop number 1. So again, step 1, step 2 is done. Loop currents are assigned, polarities are assigned. Now let's start the format approach. So I1, bracket open, and then add all the resistors. So 1 plus 1. That's all for loop 1. And then minus I2, just 1. Again, didn't need that bracket. And equal to all the voltage sources. It will be 2 volts minus 4 volts. Okay. Now let's simplify. So we have 2 I1 and minus I2 is equal to minus 2. That's equation 1. Now for equation 2, again let's start with minus I1 first. So minus I1. Just a minute. Since this is a 3 equation problem, I'll just add a, wait, let me erase this. To make it simpler when we plug the values in the calculator, I'll just add a 0 here. Okay, equal to -2. So basically x, y, and z. Now let's do loop number 2. So loop number 2 will be -1 here, then just 1. Again, did not need the bracket. I don't know, I keep putting the brackets. So -i1 and then plus i2, which will be 1 plus 2 plus 3. Now 2 and 3 has a relation through the 3 ohm resistor here, so we'll have another minus i3 times what? Times just 3. Again, an unnecessary bracket, equal to, there's just 4 volts within loop 2, so, and that 4 volt will be positive because current enters through the negative side, equal to plus. And let's rearrange that. We have i1, just minus i1, and then plus 6i2, and then minus 3i3 is equal to 4. That's equation 2. Now for loop 3, we'll put i2 first. First we'll put a 0. This was supposed to be i1, but there's no i1 for loop 3, so it's 0. And then we put a minus i2, and it'll be 3. Finally, I did not put an unnecessary bracket. So 3 and plus i3 times all the resistors, which is just 3 and 4. So 3 plus 4 equal to all the voltages, which is just plus 2 volts. So 2. Okay. Now rearrange them. We'll keep the 0 for simplicity's sake. Minus 3i2 and plus 7i3 is equal to 2. Okay. Yeah. That's equation 3. Now we have 3 linear equations. We can solve that in calculator 2. Let's solve it. 2 minus 1, 0, minus 2. And then minus 1, 6, minus 3, 4. And 0, minus 3, 7, and 2. Right. So we have I1. I'll write the answers here. I1 is equal to minus 0.54 ampere, minus 0.54 ampere. I2 is equal to 0.92 ampere, 0.92 ampere, and I3 is equal to 0.68 amperes, 0.68 amperes. All right. Now we have one last question, one last practice question. Okay, now it's again 3 loops, but in a little different orientation. No worries, it's all easy. Engineering is easy with black coffee. Now step 1 and step 2 is done. Loop currents assigned, polarities assigned. Now notice one thing that is different from the previous question. In this question, loop 1 and loop 2 had a relation. Loop 2 and loop 3 had a relation, but 1 and 3 didn't have a relation. But in this one, all 3 of them are related to each other. 1 is related to 2 and 3, and then again 2 is related to 1 and 3. 3 is related to both of 1 and 2. Okay, so that's the only difference here. So there will be no zeros. No zeros like the ones we had here and here. Let's start with loop 1. So I1, again, format approach makes life easier. Learn format approach. So I1 bracket open, and then add all the resistors. So 8 plus 3, and then minus I2 and just 3, and then again minus I3 and just 8, equal to just plus 15 volts. Okay, now 3 plus 8 is 11 I1 minus 3 I2 minus 8 I3 is equal to 15. That's equation 1 for us. Now loop 2, so again we put minus I1 in the front for simplicity's sake. Minus I1, and there's only 3 ohm between I1 and I2, so that's it. And then plus I2 and all the resistors, so 3 plus 5 plus 2, and then again minus I3 and just 5 ohm, okay, equal to no voltage sources within loop 2, so it's 0. Now let's simplify this. So minus 3 I1 plus 10 I2 and then minus 5 I3 is equal to 0. That's equation 2. Okay, now equation 3, again we start with I1, the minus I1. Remember, for loop number 1, only I1 will be positive, everything else will be negative. For loop number 2, only I2 will be positive, everything else will be negative. And similarly for loop number 3, only I3 will be positive, everything else will be negative. So minus I1 open bracket, and only 8 is between I1 and I3, right? Between loop 1 and loop 3. So we put 8. Again, I put an unnecessary bracket. Come on, get rid of this. Okay, I1 times 8. And then minus I2 and times 5. And then plus I3 open bracket and everything else. So 10 plus 5 plus 8 plus 10. 5 plus 8 plus 10 equal to no voltage sources in loop 3, so 0. Okay, let's simplify this. So minus 8 I1 minus 5 I2 plus 23 I3. 23 I3 is equal to 0. That's equation 3. Okay, write the answers here. Now we have 3 linear equations again. Let's put them in the calculator. So 11 minus 3, minus 3 minus 8, 15, and then minus 3, 10, minus 5, 0, and minus 8 minus 5 is 23 and 0. So we have I1 is equal to 2.63 amperes. I2 is equal to 1.4 amperes. And I3 is equal to 1.22 amperes. 1.22 amperes. That is the end.